You're listening to WonderLabs, filling your ear holes with nerdy goodness.
Hello and welcome to WonderLabs. I'm Ellie Mackay.
And I'm Chris Richardson.
Today we're talking with Youssef Ibrahim. Youssef is a researcher at Imperial College, and in this episode we explore his work on 3D printing.
We learn how different types of 3D printing work, as well as discussing bio-inspired design and the potential medical applications of smart materials.
We also discover how an increasingly high-tech world has the potential to reform the manufacturing industry by drastically improving its efficiency.
It was fascinating finding out so much more detail around 3D printing, and we hope you enjoy exploring the topic as much as we did. Yousef, thanks for coming on the show.
No problem.
So, if you could just kick things off and tell us a little bit about your background and how you got into your current work.
So I'm originally from Egypt, sort of lived most of my childhood in Egypt and then moved to Kuwait and spent my teenage years there. And that's when I got really into, engineering and science. Mm-hmm. And even though there wasn't really much science and engineering going on, I just sort of had an intrinsic interest in that sort of thing. And I think that's what sort of kicked it off at that age. So I started off my undergrad mechanical engineering at Imperial as well. I actually got more passionate about the trade after I graduated from my undergrad. When I went on to postgrad, you can chase your interests a bit more. So I had actually done a little bit of 3D printing in my undergrad. Yeah. That was my first introduction to 3D printing. And essentially all it does is it takes a 3D model that you create on your computer. Mm-hmm. And they've made all these sort of entry-level software that can do that now.
And computer-aided design.
Yeah, CAD or CAD.
Yeah, it's mostly CAD.
So you sort of draw something online in a 3D space online, you kind of create something and then you press print.
Yeah, literally. So to boil it down, you just press print and, it's a printer. So you can just think of it as a normal paper printer. It simply just takes that 3D model and cuts it down into slices. Slices it up into super thin, really thin 2D
so just in the
sections.
Same way when you have an ink and paper printer, you see it printing sort of
lines
line
and
lines of the text and then the image appears. It's basically the same thing.
Yeah, exactly. Same thing, but in 3D.
It's pretty cool.
So rapid prototyping is actually you
can't
use the word the better though. As in, so rapid prototyping that was existing for, normally you get a basic version and then you get developments of better and more universally usable. But actually this is kind of the opposite, where the industry and serious things would still use rapid prototyping because that is still the original best robust
it's an industrial process
industrial result, whereas so the 3D printing is more of a step down to kind of public use, home, high street level.
Exactly.
It's different applications, I suppose.
And it's mostly for ornamentals or like phone cases or anything that's sort of low tech, I would say.
I've read about lots of different materials can be used because they're now using like biodegradable materials or recycled plastics in 3D printing. So are there lots of different types? Because I've seen some that kind of use like is it silicon powder, like a kind of sand-based powder?
So there's been lots of innovation in that field. So initially it was just two types of plastic that you could use, and obviously that's not ideal. So they've branched out into like conductive materials, like because obviously you can't print metal or any metallic objects in the same way. So they generated sort of like wooden materials and elastic, like rubbery type materials that you can print in the same way, and transparent materials, biodegradable materials, and so on. There's quite a big variety of materials you could use now.
So your current research then, how does that fit into the space?
So I'm working mostly in the aerospace and medical implant industries, and it is a metallic printer instead. So it uses a metal powder, very fine powdered metal essentially is burnt and stuck together.
Wow, so you take like a block of what's your raw material that you order that comes in?
Just powdered metal, so just bottles of titanium or whatever.
Yeah.
But this time it's just with a laser that melts the material together.
And does it melt the metal directly together, or is there some sort of glue?
No, it melts the metal itself.
So the only ingredient is
the metal.
The metal.
It's called SLM.
Sorry,
it's referred to as SLM, so selective laser melting.
Selective laser melting.
Yeah.
That's cool.
So many new acronyms.
Yeah.
We love some good acronyms.
And is stainless steel the normal metal?
Well, stainless steel is what I use personally because it's a cheap ish material. But there's a few materials, and you can do gold and silver, and it's to do with firstly how the material corrodes, right? So gold is obviously very resistant to corrosion and it will last for a long time. And secondly, how easy it is to get them out of the ground, So gold's obviously rare, it's hard to find. Steel is iron, is fairly easy to extract. Doesn't take that much energy to extract it. But obviously it does corrode and rust very quickly. So if you had a 1,000-pound block of iron sitting in your safe or whatever, after a few years it will. Well, if you're not careful, it will deteriorate and it'll lose mass. And that means you lose money.
And that's really interesting as well, because that means, we're valuing longevity in that case, whereas the rest of our lives is all about consumerism and waste and quick results and things that last for a day and then they fall apart and break and you buy a new one. And it's, the majority of our lives seems to be tending towards replaceability and short, non-sustainable materials. But then when it comes to metals, we like the gold and the long-lasting materials more than the degradable ones, which is kind of...
I think it's a historic thing, because that's how people used to store their wealth.
Exactly. Absolutely.
Yeah. You don't use plastic to store your wealth.
Well, I guess until
unless you have a credit card, but
that's true.
you
So again, to compare it to the traditional assembly line, there would presumably be quite a lot of waste in an assembly line.
Yeah, so that's one good thing about the 3D printing process.
You just sweep up all the powder that's not used.
Yeah,
like when you did those glitter projects when you were little.
Oh yeah, all of those glitter projects that I did.
And you tip it and then you sweep and you reuse the glitter.
Yeah, exactly. Good analogy. You save that material you haven't used and you just put it back through the machine.
And so 3D printing in general, though, you said is relatively cheap compared to like the assembly line.
Yeah, it's
is that because of the
wastage,
the waste
mostly. Yeah. So you have this thing called the buy to fly ratio when you're making a
what, sorry?
A buy to fly ratio.
Okay.
Yeah, and that essentially just gives you a ratio between the stock material you buy and how much of it actually ends up in the component that goes on the airplane.
Okay, wow.
Generally, you're talking about a buy-to-fly ratio of 30. So you're essentially
30 to 1.
You're wasting all that material just in
for
conventional manufacturing.
I don't know, a gram of my iPhone.
Yeah, exactly.
There's 30 grams worth of raw material
of
insane
iPhone.
Wow.
or aluminium or whatever.
That's kind of crazy.
You can then go down to about 1-to-1. With 3D printing.
Is it really 1-to-1?
Very close to 1-to-1.
I was thinking maybe you'd get down to like 5-to-1 or something, or 2-to-1.
Well, it also depends on the material, because for some materials are very reactive. So titanium, for example, is highly reactive, and you actually have to do the whole process in an inert environment so it doesn't oxidize. And that's mainly how you lose the material. So it oxidizes, so it burns essentially.
You lose some.
So that's how you lose
some burns off.
Yeah, but when you machine something, you're throwing away all that waste, which is sort of difficult to use.
So that's astonishing. So the fact that you could be at almost 1-to-1 ratio
almost efficient,
that's amazing. Because in terms of efficiency in the natural world, we lose in terms of like energy retention. It's famously inefficient, and
no perfect process.
The most efficient process on the planet, which is photosynthesis, is still only about 1% efficiency. And that's obviously in terms of energy, and presumably the energy losses in 3D printing are still relatively high if you looked at energy in versus the amount of energy in the product.
Well, that's also another advantage as well. Is you're using a highly concentrated laser, and whenever you concentrate the energy, you're losing less of it. So in terms of the energy usage as well. So
this really is efficient. It's
much more efficient.
Economically, in terms of energy, it really is kind of amazing.
And you get to use lasers.
Very cool.
Which does sound very cool.
Yeah.
Laser is another acronym, actually.
It is light amplification by stimulated emission of radiation.
Boom.
I learned that one recently as well. Yeah.
That was my password, I think, on my computer file.
So if you want to hack into Yousefs accounts, everybody, just
from about 10 years ago. Go for it.
So in your research then, you're working on something called microcells.
Yeah, or lattice structures.
Lattice structures. Can you tell us about lattice structures and microcells?
So you can think of a lattice structure as a foam. I think that's the most sort of relatable analogies. They actually are called foams as well.
Yeah.
And that just means that it has lots of air in it. Right. So it's not a solid block of material. It's material with lots of holes.
And what's the benefit of that?
And essentially, you're just making it much lighter,
Yeah.
and you're using a lot less material. So for comparable sized components, if you have a one that's made of a lattice structure and one that's a solid piece of material, you're talking about a 13% the weight of the full block, or even less.
And so I think maybe a common misconception at this point might be that material is then weaker, because if you think about a sponge or foam, foam is a soft, squishy thing.
Yeah.
Whereas
drizzled over your Michelin stars.
Yeah. Whereas like a solid block of metal, you'd think, oh, well, that's going to be stronger than a lattice structure. But if we look at carbon lattices, if we look at diamond, for example, that's a lattice in its structure.
Yeah.
And that's very, very strong material, one of the hardest material on the planet. So can you just maybe discuss how lattices and these kind of structures, these air-filled structures, what their strength is like?
So generally speaking, that is true. So they are much weaker usually, and it does sort of scale to their relative density or their relative mass.
Percentage of air in
exactly.
how foamy
the porosity
they are.
and the
porosity. There you go.
Yeah.
Not foamy.
Foaminess.
Porosity. Yeah.
And it generally does get weaker as you have less material in there. But
Sure.
the whole point of my research is to essentially figure out the optimal way to place the material in there so that it doesn't actually compromise any of that strength. So you maintain the weight reduction aspect of it without losing too much on on the strength side.
So again, you're sort of stripping down and increasing efficiency.
It is, yeah. That is the absolute sort of the ultimate version of material efficiency is you put it exactly where it has to be, and when you think of a block of steel, if it's supporting a weight on top of it, not all of the steel is actually doing any of all of the work. So only certain parts of the steel, based on the angle of loading and so on, that's actually doing the
point
supporting.
Loading and everything.
Yeah.
And it's worth thinking as well, because all materials are arguably lattices on a molecular level.
Yeah.
So this is just sort of scaling up that porosity to a bigger scale.
Essentially,
But you can still kind of harness that idea of, a triangular force being very, very strong.
Exactly. So triangle lattices are actually are one of the best sort of stiffness to weight ratios you can get.
Is that the same thing as how you can stand on an egg in one direction but not in the other direction? Is
sort
that
of, yeah.
To do with it?
It is sort of.
It's all about distribution of.
Yeah.
The
so
weight.
you want to spread out that.
No, should we try it? We should try it, shouldn't we? Coming next.
It's
next
very
episode,
difficult.
Chris and I crushing loads of eggs
in Ellie's house.
Have you tried it?
Kind of, yeah. I've tried it in my first year of undergrad. Actually, we tried messing around with that a little bit, but it is very sensitive to exactly making sure the egg is upright. And, it does work on a similar
That's
principle.
exactly just right. The Goldilocks egg fact.
Sorry. So essentially, that's what you're trying to do. You're trying to find that sweet spot in the egg of any material. You're trying to find that pivot point,
that shape,
that will send the force equilaterally through the material so that you don't get any individual fault structures. I'm thinking as a geologist in terms of fault lines.
They're called stress concentrations.
Yeah.
So you wanna avoid any stress concentrators in there. And that's sort of it's a design sort of project.
That's really cool.
It's a very mathematical, very computational project.
How much of it involves you visualizing things in your head and on a computer before these structures are then built?
It actually is a lot of visualizing and sort of just sitting in a dark room and trying to think of those shapes. But obviously that's just a starting point. So it's kind of nearly impossible to visualize the best possible structure in a certain condition, right? And it's more of a trial and error approach as well when you're designing those shapes, is that you just let a computer design, multiple shapes and it'll keep iterating.
So do you you throw in all the components into it and sort of press go and
all the parameters.
And it'll
that's one way of
shift around and try and figure something. So then the computer tells you this is the strongest. Does the computer then do all the sums of every possible angle and calculating the forces? And that's amazing.
I love the efficiency of it, but I still love this image of the engineer of the scientist in this dark room,
sitting in a dark room, drawing on a napkin, trying to figure out the numbers,
trying to come to some conclusion about what the best thing is.
You do get a lot of inspiration from like you said, so like the carbon sort of diamond structure and those molecular structures. They are optimized, So
exactly.
Nature's kind of done the job for us already,
done
right?
the job for you.
So you base a lot of that on. So there's loads of
And that's because my next question was going to be: does the computer come up with something completely novel ever, or like a novel shape? And this was,
or does it just mimic nature?
Yeah, because this was something I found really interesting. I went to a talk about snail shell development and actually all bivalve mollusk development, and how they use computer models now to grow different possible shapes, and every single variant of mollusk shell, and the tightness of the coil and the number of loops and the angle, and whether it's long and thin or short and fat, and all of that all comes from an XYZ plane, which is just the growth is faster in one direction than the other, and then this model went through and in 20 minutes came up with sequentially the evolutionary history of, try this shape first, no, this shape is better, no, that shape is better, now this shape is better, and it followed the exact fossil record. But then it went 2 steps further and it came up with 2 shapes of shell that haven't been invented yet in nature, but they then found those in the evolutionary record as well. So it's like we're kind of predicting where evolution will continue. Is it similar to that with what you do?
Yeah, it is very similar. So yeah, it is definitely a good way of doing it, because it is actually it's called a genetic algorithm method, right? So they are process of nature.
A Darwinian approach to
it is
materials,
and it's not just materials. It can use it. Cool. You can use it to solve anything.
Process of elimination, I guess, ties into it as well.
Everything.
Trial and error.
Actually, if you apply this,
computational
exactly, you can apply the algorithm to pretty much anything, and just this entire notion that something that is an improvement on the last iteration or variation, and then using that to move forward into the next generation.
Yeah,
that makes so much sense intuitively.
Yeah, and from an educational point of view, I like it because it's the idea of success comes from 1,000 failures, and trial and error being really key to development. And you can't ever progress if you are a perfectionist and you get it right. You wait until everything's perfect. No, it's true though. Like failure and learning from failure and learning from mistakes and reflection and then tweaking,
it's that
and
polarizing moment.
Gradually improving, and that stepwise improvement is really key to everything.
It is how nature did things, and the evolutionary method is gathered a bit more momentum recently, and just because of the computational power available has increased, and now you can actually start to mimic that natural process.
Amazing.
Perfect.
So
that
leads
really
us
on
nice.
very nicely to our next set of questions.
What you're describing, this term that seems to be thrown around a fair bit in this world, is something that's bio-inspired. So you've described your methods, your methods of design as being bio-inspired. What does that mean then? Is that
such a cool word?
So you're essentially just following nature's lead in different aspects as well. So mimicking the actual bio shapes or biogeometries that have already been solved. So you look at a bone, for example, an animal bone, you can see how on the inside it's a bit foamy as well, and it is sort of
foamy bones.
Yeah, all
makes
bones.
Me feel all jiggly wiggly.
All bones most bones are made up of pores.
But that's good because that reinforces literally the idea that we're talking about. Foam is not a soft material. Of foam, we mean a hard lattice structure.
I mean, bone is one thing, but wood is a foam as well. Yeah, technically. So, and anything wooden, it is on the inside.
There you go. Wood is a foam. That's
heard it here first.
And that's how they discovered cells. When they're looking at cork,
of course,
as a bone.
And because we're talking today all about efficiency and why reinvent the wheel. With all this technology and computer algorithms and artificial intelligence and machine learning and that kind of thing, robots taking over the world. Are we ever going to come up with something that doesn't already exist in nature, or are we just recycling the natural world?
Is that a bad thing? Yeah, as well, I suppose, exactly. If it has done it right.
So maybe there's all kinds of stuff out there that we still haven't used from nature.
Yeah, definitely. There's just countless mechanisms, and even on the micro scales that can be translated up to the macro scales. For like vehicles and so on. You could copy how bacteria move, or there's just loads of solutions out there waiting for us to be found, and it is sort of a difficult question to answer whether or not we'll ever come up with something that's totally new.
And even if we think it's novel, it still exists out there somewhere in the deep ocean. We just haven't seen it yet because they've got billions of years head start.
Yeah. Earlier on, you sort of touched briefly on sort of medical and aerospace. And is that kind of where your work is situated in terms of applications then?
Yeah, so that's sort of what inspired the project, and those two industries stand to benefit from this particular application of 3D printing.
Mm-hmm.
In the aerospace, you're obviously dealing with much lighter components, and you're wasting less valuable material.
Hashtag efficiency again.
So we can have cheaper flight tickets for all of us then soon.
Well, yeah, and also use less fuel.
So, right, it's a big environmental component there as well.
Because for every kilogram you cut down, you save massive amounts of fuel, and that
and it's huge, isn't it? It's something. It's this crazy ratio that for every.
It is a crazy ratio. I can't
do you know
remember off the top of my head.
Whatever, something like every gram that you lose in weight is however much. How many litres of fuel? It's crazy inefficient.
That highlights to me just this seemingly so far disconnected activity that's taking place in a lab in Imperial College can actually have this massive environmental consequence in a really positive way.
Yeah, absolutely.
And again, that just highlights the importance of research in all of these seemingly disconnected fields and how interconnected they all really are. If you have the right kind of brain focusing on the potential applications for it.
You can imagine in 10 or 20 years or however long, looking back and trying to explain to somebody how you used to make an aeroplane. We used to start off with 5,000 tons of material and 50 different machines and assembly line, and we used to cut it down and waste and throw this away and throw that away. And we ended up with something that was so heavy,
get off the ground.
we had to pay thousands of pounds of fuel and drag rocks out of the ground to burn them to get it into the... Whereas nowadays, we just press print on our clever machine.
Now we knock you out cold, and then we 3D print you out in the Bahamas, and your consciousness just continues.
Maybe more than 20 years for that.
Probably more, yeah.
And so are we then going to end up with like titanium planes?
They already are titanium. Titanium is very attractive in planes because it's sort of similar to aluminium. So they use aluminium in planes as well because it's obviously a lighter material that's resistant to corrosion. Titanium is the same, so it is very light, but it's much stronger than aluminium. So that's why it's attractive.
This may be a silly question, but would you end up potentially with planes being able to be made in kind of out of one single piece of material?
Well, that's sort of aero research, and that is a big field to also making a sort of a unicoque plane.
So it's not a silly question then.
No.
No, that's why having less parts connected together. That's always a goal in engineering, because you want to have as little parts as possible.
Fewer chances of mistakes or error.
Or fewer chances of failure, because usually when parts connect, that's
the point of failure.
One of the weak points in the structure, and you want to make it, if you can make it into one piece, that would be ideal.
The dream.
Could you 3D print a diamond plane?
What do you mean by diamond? It's an actual diamond.
Now we all get into the realm of the silly question, which is good.
So I saw about planes that have a glass bottom. It was in the first class section of a plane, and it's got a glass bottom, and you can play golf on the glass. Yeah, no, I don't think it's real. It's a conceptual thing, and I was thinking, how cool would that be to have a...
That sounds terrifying.
A diamond, because I was thinking in like Jules Verne, like Journey to the Centre of the Earth, and having a capsule made of diamond, and then it's good because it's transparent, so you can sit in there and you can look outside at all the lava and figure out what's going on.
And you'd be absolutely fine.
And you'd be fine.
A little diamond plane.
So can we get a diamond capsule of some kind, please? When can I order that?
I don't think you can 3D print it. It can probably generate it some other way, but we do have a very similar material, which is crystal sapphire. Right? So
crystal sapphire.
Sounds good.
I already want that.
Is essentially
the new best friend.
It's a very hard material. It's aluminium oxide basically. So you just get.
That sounds less cool when you say it like that.
Crystal sapphire. That's a marketing ploy. That right there.
Yeah, the geo science name of it. And they make windows out of it for sort of high pressure and high temperature environments. So for furnaces and deep sea submarines and that sort of thing. Damn. The windows are all crystal sapphire, and my watch as well. So the surface.
This watch is crystal sapphire.
That's crystal sapphire.
So if I tap it will not break.
Yeah, you can do whatever you want. It's very tough. Doesn't scratch.
I mean, what are you doing that requires you to have a crystal sapphire watch?
Just scratch resistance.
Scratch resistance, okay. So it's not because I was going to say surely your bones would crush at if you went
I'm not going to go
diving.
Go into battle with this.
So that would survive. Wow.
On the silly questions front, though, there is a genuine conceptual question, I think, that is a bit more grounded in current affairs. So Ellie's had a problem with her tooth recently, a dodgy pistachio nut.
Yeah, I cracked a tooth.
We were wondering, actually.
My face, the listeners can't see, but my face is hideously swollen.
It's alright, it's not that hideous. Well, on a scale of 0 to like John Merrick, 0 to 7.
0 to John Merrick, that's really mean. Ow. But actually when I laugh it hurts.
Could we 3D print a tooth?
Yeah, well, that brings me on to the other aspect of my research is bone implants and sort of replacement parts for people and animals.
Yes, please.
And
where do I sign? Because I'm in a lot of pain. When can I get my new tooth?
Well, I'd say in about 20 to 30 years. But
really?
To be honest, the machine that we use, the machine that we're currently using for our research that prints titanium and steel, that is also made for dental applications.
Oh, really?
So for printing, crowns and so on.
Oh,
sure.
Yeah.
Bones and
titanium
teeth, kind of related.
And it is a real application of this sort of thing. And obviously because of the bespoke nature of anything that needs to go on a person is that and that scale every end is different.
Yeah. Well, that's amazing though.
But so why 20, 30 years? Because I would have thought that a tooth is fairly easy to, in terms of the shape, you can create false teeth.
Yeah, you could.
From 3D printing. And if the technology to print bone is, it's underway.
It is, yeah, but the longevity of it is untested. So we have no idea how long these parts will last. The actual process.
So the next time I eat another pistachio, it'll be just gone again.
You better
just blend them first into like a pistachio
just eat
paste or smoothie.
You're just telling me I have to eat soft foods from now on.
It's
not that old.
I'm not your doctor, but it's...
but it's untested.
Okay.
So that's why.
And so then let's talk more, moving away from my broken tooth. What is the use of this? So what specifically are you doing with 3D printing bone research?
So a few of my colleagues working in this field, they essentially are looking at matching the stiffness of bone to the implant. So the stiffness is essentially obviously how much the material deflects under load, right?
Yeah.
And usually with normal implants is that it's a solid block of titanium or cobalt chrome.
Sure. So this is if you have an artificial hip replacement.
Exactly. Hips are one of the main applications in this case, and obviously because the implant itself is so much harder when you're loading your legs, when you're standing on your leg, the implant will deflect less than your actual bone because your bone is softer.
Because bones are actually sort of bendy in a way, aren't they? And we don't want brittle bones.
Bendy.
Yeah.
And that scale.
Yeah,
exactly. Yeah. So essentially, what you're doing is that if you could have that lattice structure inside to essentially lower the stiffness of the implant, so that it's the same as the bone, right? Then the bone and the implant will move together more in unison.
Cool, yeah.
I like that.
And that essentially decreases the likelihood of the implant coming loose.
Yeah,
that's awesome.
A common problem nowadays is that you have to keep replacing the implant every few years because it comes loose no matter what you do, just because
of the
one of the reasons is that stiffness matching, so
that's very cool.
That's an application
and
of it.
So this is still using like a metallic foam structure, this lattice.
Yeah.
So it's still a metal, it's not an organic, it's not a bone material. You're not like using powdered bone to build bone. Potentially, are we going to end up in a position where the materials that we're printing are better than bone? Because this metallic foam structure is not going to develop bone cancer, and it's maybe not going to shatter or break so easily.
The problem, obviously, with that is that having a living tissue, part is better because it's continuously adapting. Right. Yeah. So the thing about bone is that it gets thicker when it needs to be, and it gets softer where it needs to be, and it's continuously changing.
So it's still a more intelligent material than even our most intelligently designed material.
Yeah, if you have a piece of steel, it's going to stay the same shape forever, or unless it rusts. So having that aspect of continuous adaptation to load and growth and so on, that's very important. And obviously if you have an implant in a younger person who's still growing. Right. They will have to replace it, even if it is matched to their bone, just because they're going to outgrow it.
Yeah, because it's a change. Oh, that's a really interesting point, isn't it? It's worth thinking about the idea of we might all want to be cyborgs in the future and have our, highly plasticized, resistant materials.
Nothing's better than living tissue, in the end of the day.
Yeah.
And from a point of view of the Mars 1 mission and this idea of we're going to be living on Mars in the next 50 years, obviously 3D printing is critical to that because we can't take everything with us.
Space is one of the the space industry and going to space is one of the main drivers of this technology. Because you can just not just print parts, but you can also print food.
I was just about to say, what about food? What's this idea of
3D printing?
Chris found this definition of 3D printed food, which I thought was horrible because it was squeezing out layers of like food pulp.
I still think the pizza sounded good.
I would not want a pizza that's been squeezed out in layers.
I'd totally go for a 3D printed
But lots of things are squeezed down in layers. And you don't even realise. But no, it's
that's a quote of the day. Lots of things are squeezed out in layers.
So what's this? What 3D printed food? What's that all about?
When you're looking at the constituents of foods like fat and carbohydrates and fiber and and breaking it down to that level and then being able to stitch those parts together in a way to generate because I actually know a person who was working on just printed hamburger patties.
Yeah, that's right. Yeah,
and they were looking at the ratio of fat to lean
muscle
lean
mass
muscle mass and putting together a patty with different ratios. So it's not essentially a layer by layer approach anymore. It's more
patty
like
by patty.
Well, you can just take, instead of taking like a bag of fruit and a bag of vegetables and a bag of meat, you can just take a powdered fat and powdered carbohydrate and put it together in a way to generate.
Well, this is my question to you then, Little Miss Vegan. So would you have an issue with it? Because I know when it's come to this debate of lab grown meat before, again a completely different approach to you is taking, say, the stem cells and then growing in a petri dish the lean muscle mass and the fat and having your beef patty produced in that way. And I know that, again, like a lot of Muslim and Jewish scholars say that they wouldn't have a problem consuming, say, pork that was produced in that way.
And a lot of animal rights, vegetarians and vegans whose their sole reason for doing it is purely for animal rights. Well, if the meat has been grown in a laboratory, it's never had sentience, it's never had...
So would you go for that then? If it had been constructed from these from these components just to try... this tasty 3D printed burger.
Well, no, I mean, it would have to be environmental. I'd have to know about the sustainability of it because my reasons behind my food choices are to do with the environment and sustainability. So if the production of that 3D printed meat patty was,
chopping down
environmentally unsustainable, then
the
same rules would apply.
Sure.
But from everything we're hearing, it sounds as if it could be a very sustainable method of food production.
Yeah, it could be.
So if that meant not chopping down half the rainforest, and instead we have a small printer that prints out food from these powdered carbohydrate vitamin substances, then given on principle I have to have no issue with it because that fits my principles, but there's an idea behind it of
it's just so wrong. I'm going to go tuck into another cricket bar.
Artificial. Well, I mean,
it's really interesting because a lot of people now are beginning to shun processed food. Or have done for a long time, and it's growing. And we want organic, we want back to nature, back to earth, and we're talking about this connection to nature. Of I'd rather go and pick an apple from a tree and eat it, and that sort of thing.
I'll 3D print it from the comfort of my own home. Thanks.
And so then this is the ultimate in processed food. No, it's completely manufactured.
But I mean, it's
processed.
The problem with processed food is that we don't know the long-term effects of the chemicals we're consuming.
Exactly.
I mean, even with this technology, once you are able to generate apples and meat in your home, we still don't know what kind of effect that would have on you down the line. 20 years down the line, 40 years down the line.
There are obviously some technical challenges that you're trying to overcome in the current hurdles of research. One of the other things that seems to come up are sort of issues around security and legislation around how do we
put
limitations on what people can manufacture from the comfort of their own home. So things like weapons and so on. And I mean, do you have any sort of comments on that?
Well, if you're going to make any usable weapons, you're going to need those big, bulky industrial machines that can print metal. For the time being, it's very difficult to print metallic.
Print my plastic stick and come and hit you over the head with it.
Yeah, exactly. Might as well just use that.
But if
use a piece of wood or something.
That's the thing. The whole it's like not being allowed to take certain things on a plane. It's like, well, I could just punch someone really hard.
I mean,
I can
I think it's just the showmanship aspect.
Just if any airline's listening, Elliot doesn't actually want to attack anybody with their fists on a plane.
I have enough trouble going through security as it is on a plane. I probably shouldn't have said that.
So these security concerns, then, you think, are probably quite unfounded, overstated, with the current.
But what about 20 years in the future, where it gets to the point where we all have, this is the dream, isn't it, that we're all going to have our own 3D printer in our house the same way that we all have a regular printer now.
Yeah.
At that point, when we are able to print metals, and we are able to, everybody can just press print, and a teenager can print drugs or guns or whatever it might be, or false ID or all sorts of things. Like for everybody who's good, it's like the internet. For every good use, there is there is
an endless number
a malicious or a bad use.
Yeah.
So does it not worry you at all?
Well, I mean, it just applies to everything, doesn't it? You know, like 3D printing is just a tool in the end of the day, you know, and you could misuse it if you want to. I mean, there are people now that you know can get you guns and knives at it.
Okay, so security aside, and you know the idea of a whole bunch of people printing guns aside, what about just the idea of the economy and how it will change consumerism and capitalism? Because if everybody's just able to print anything they need, then what happens in terms of business?
If it leads to the fall of capitalism, that can only be a good thing in my eyes.
Yeah, mine too. It is potentially a disruptive technology. But
yeah, for sure.
I think
print your own Uber and print your own Airbnb to stay in on the beach. And print your own pizza and write a review about it on TripAdvisor. And then...
But aren't we then putting the power back into those who own the raw materials? The mining companies and the iron ore and the metal ore.
But I think because we went through that, you know, historically already, there's already, you know, infrastructure in place to make sure that no one has a real monopoly and no centralized unit's going to be responsible for that scale of access to manufacturing. And I think
it's not going to be a kingpin of crystal sapphire somewhere.
I mean, there already is probably, but you know, I don't see that as being a problem really. I think at this current stage of technology, it's not possible at all to be able to replace the usual way of manufacturing things completely just yet. But
so there you go. You heard it from the horse's mouth. There's nothing to worry about.
But with Youssef Ibrahim at the helm, working on the stuff, we can expect 20 years to be knocked down to just a few.
Yeah.
I'll try my best.
Awesome.
Well, that's an exciting. It's an exciting picture of the future that you've painted for us. I'm looking forward to it.
Yeah, for sure. And like all the applications that we've seen already, like I'm looking forward to seeing what else comes out.
Yeah, really, really fascinating. Thank you very much.
Thank you.
No problem.
So we want to finish on some rapid fire questions for you. We've got a few quick questions just to finish off.
Okay.
And so just to start off, if you weren't doing what you're doing, what would you be doing instead?
I think I'd probably be a musician.
Yes. High fives. I think that's what almost everybody that we've had so far has said.
Well, yeah, because I think it also stems from my engineering, you know, interest that I've always been interested in how musical instruments work.
And you're a drummer, aren't you?
I am, yeah.
Yeah. So that's quite a tactile,
it is
3D...
very hardware, you know, there's a lot of hardware involved. And you know, it does play into my interest in engineering.
Awesome.
Brilliant, thank you.
Is there an emerging field or technology that you're really excited about?
I'm really interested in VR and you know, augmented reality and that sort of thing. I've always, you know, imagined that as a kid, that, you know, if you could generate any world you want in your living room, then that would be great. And I think they're making great leaps and strides in that technology right now. And I can't wait to see where it ends up. You know.
For sure. I mean, hypothetically, if we get to a point where you realise 3D printing is at its limits, you could always just pop on your VR headset and then 3D print all the stuff you wish you could 3D print in reality. So.
Well, there is like VR apps that you could do to actually make parts in VR.
Really?
And then print them, you know. So actually, that was...
so glad. That's so
Wait, so you go in your headset, that's where you sculpt the model.
Yeah.
So you are becoming the CAD.
You are the CAD.
Oh, that's cool.
Okay.
Self-CADing.
And I think that's
AutoCAD.
That's actually been around for a while. Like, there was this group of artists that you know, just go into a VR world and just sculpt in real time, you know, a sculpture, and just the machine is recreating
and collaboratively, so 2 or 3 of them.
Yeah, more than one person can come
together.
in. They have magic wands.
So in terms of something like car design, because I was speaking
car
to
is very applicable here actually.
I was speaking to a car designer who was telling me that they still, I mean, he uses AutoCAD of course, but he still goes back to carving the foam because they have the design, but then they have to take it from that. They 3D print a foam prototype model.
The body. Yeah.
To be able to just see you've got to be able to stand and walk around the life-sized car and see what it looks like and how it works and how it fits and so on. But so they could do that in a virtual space.
Yeah,
and then carve a little section off and trim the wing mirrors down. And
literally, they could do that. And
that's
also
cool.
Amazing.
there's also a training version of that. So for people who like do maintenance in the cars and so on, I think that's already a company right now that just trains you in virtually how to take the car apart.
So you can't, if you mess it up, it's not the end of the world. And the same, of course, with surgery as well. Training.
Yeah, of course. Yeah, there's real life trade, training on VR going on right now.
Okay, is there a science topic that you find is frustratingly misunderstood, that if you could sort of wave a magic wand and everybody would understand that topic? Is there something that you find yourself thinking, I wish people... You constantly have to explain something? Or...
Physics and a few physics principles are can be heavily misunderstood, and when you understand them properly and go deep into them, they're just much more fascinating than people really think.
Just like the fundamental principles.
Yeah, really fundamental.
So pay attention in your physics A levels is what you're saying.
Yeah.
Or your physics GCSE. Okay.
Physics is fascinating.
Do you remember a particular moment when you were first fascinated by science or engineering?
I do, actually. And it was actually a piano that really got me into
that fusion of music and engineering again.
Yeah, that goes just as far as my interest in the physical world. And I was always fascinated every time I sort of found a hidden piano in someone's house. That really that was sort of the highlight of my day.
What age were you at this point? Do you remember?
I think I was about 5, 6. And that's one of my earliest memories.
And you were just drawn to the idea of a piano and how it worked. I was just drawn and what the hell's going on inside. That makes it sound like that.
Huh. Did you clamber inside and see what was going on?
This is where you admit
I wasn't usually allowed to do that.
All of your family and friends' pianos that broke when you were a child.
All of his broken pianos.
Yeah, I have broken multiple pianos more than I care to admit. It's quite childish.
That's very cool. Do you have a piano in your house now?
No.
Because you can't risk it. It would be in pieces.
Oh, yeah, that's one aspect of it, But
3D print one.
Yeah, eventually I will 3D print one. And that was one of my goals at some point. But
amazing.
We'll see.
Okay, so we always ask people if they have a favourite piece of lab equipment. Now, you only work with one piece of equipment, which is a 3D printer. But do you have? Is there some other element of other than? I think you're not allowed to say 3D printing because that's cheating.
I seem to have an affinity just for this. There's a particular machine that just pulls things apart in the
we call it the Yousefs
in the lab, and that's one of the most basic engineering sort of is it's essentially just pulls materials up until they break, and you just measure how much force it takes and so on for them to break and extend.
Amazing.
And I just love messing around with those machines. Just sticking
what's
just
it
put
called?
Everything in there. Yeah, what's it called?
Well, it's called a tensile test machine, or
a tensile test machine,
TTM. I guess you call it that.
Awesome.
What have you put in there? What sort of things have you pulled apart?
I've put Allen wrenches in there. I've put screwdrivers. I've stuck
enemies.
Well, they're usually a bit too small to put people in, unfortunately.
What's the strangest thing you've put in a tensile strength machine?
I don't think I actually got too adventurous because they belong to the university usually, and I can't really mess around with them all the way.
Let's respect the university's property, of course. Yeah.
I mean, you're not meant to put Allen wrenches and screwdrivers in them anyways.
We won't tell them.
But they can handle it.
Last one, and this is famously the tricky one. Do you have a favourite science joke?
Oh no. Well, I'll have to think about this for a little bit. Well, there's one that's a bit dark, I guess, but
that's all right.
We like that.
So, two chemists walk into a bar, and one of them says, "Can I please have an H2O?" And his friend says, "I'll have an H2O too," and his friend dies.
It's water and hydrogen peroxide, aka bleach. Don't drink bleach, kids. Yousef, thank you so much.
Oh, so silly. No problem. You're listening to WonderLabs, printing your lattice holes with metallic foaminess.
Excellent.